Okay, so this is the day 2 video. Sorry again about not making the day 1 video the way I would have liked to have done it. Here we are on day 2, which is 8.3 and 8.4. All right, so how many different 5-letter... You know what? I'm going to, like I always do, I'm going to save this for class. We'll do this warm-up in class. All right, two-way frequency tables. So this is a very popular way to give out data that kind of comes in multiple variables. I'm putting this those lines there to kind of separate out the totals in the total columns, just so you can kind of see that. They don't always give you places to stick totals. Sometimes you'll just see a 2x2 grid that doesn't have the total row totals and column totals kind of in there. So put those in if you don't see them. Anyway, this thing is called a two-way frequency table. And yeah, two-way because there's two variables, and these numbers in here stand for the counts that kind of belong in the intersection of the two categories for the two variables. All right, so it's pretty easy to understand the context here. Complete the table by filling in the missing values. All right, so if this is the total down here, all I have to do is subtract to figure out that this one is 25, and this, then if I kind of add this way, and you can do this in any order, that should work no matter what. If I add that way, sorry, I'm looking at another screen. This one should be 84, 60 minus, like you, again, any order you kind of want to do that. That would have to be 76. 76 minus 44 is 32. 32 plus 59 is 91. And if I did it right, I can add that way and it adds up. Great, it does. All right, so fill that in, not too hard. Now, find the probability that a randomly selected student from the sample is. Okay, the hardest thing about these, because they do get kind of complicated, is what to think about for the denominator. And as we learned in the first day's worth of stuff, the denominator is the total number of possibilities, or like the sample space. So this is probably the most important part of that phrase, which is from the sample. And so, yeah, these are, and I do this first, I teach this in AP Stats. I would put the out of 160 in all of these. Wait a second. They changed it up on number 2, I can tell already. If there's no reason for them to change, if there's no reason to change it, go ahead and just think of this is yeah, from the sample total, there's no changing in who it's out of. It's just going to be out of 160. And I think that kind of helps focus your hunt for the numerator. So out of 160, how many are seniors? 76. Okay, that was a long explanation. A junior not attending the prom. Again, out of 160, I thought I saw something interesting there. It's not as interesting. I thought junior not attending the prom. So out of 160, we got juniors not attending the prom. That's right there, the 59. Those are the juniors not attending the prom. And just not attending the prom in general out of 160, that is the 91. If a student was randomly selected from the seniors, okay, there we go. There we're changing the denominator. So just out of the seniors, that's the thing that's going to get people. What's the likelihood that they're attending the prom? So this is kind of like a conditional probability that given that they are a senior. That's 44. People who get this wrong are probably going to say 44 out of 160, and they miss the from the seniors. So if we already know the person's a senior, we can narrow that down. It's only out of 76. Okay. Same thing. I think I will do this one in class because it's exactly the same idea. It's just a second example. Venn diagrams. Okay, hopefully you've seen these before in your life. They're pretty self-explanatory. What people kind of forget about Venn diagrams is that if you just kind of came up to someone, or you saw this Venn diagram the first time and said, how many people take Spanish? Sorry, that was weird. People would probably say 124. Well, be careful. That also includes the 37. So there's actually, what is this, 161 people take Spanish. I do this on my Venn diagram just to kind of be careful about it. Calculator starting up. So this is 5. Is this 215? Yeah. Just in case there's a question about Mandarin, I don't accidentally just go 178. It's actually 215. Okay, so let's be careful about this. 366 students. Oh, yeah. I also kind of like to write the total sometimes. 366. That's good. All right. So which language classes they attend? So some take both. Some take one or the other. Some don't take either. That's what this 27 is about. What's the probability somebody took Spanish? Okay, so this is out of 3, so it's selected at random from the whole sample. So out of 366, how many take Spanish? I'm glad I have that 161 sitting there. How many took Mandarin? 215. How many took Spanish and Mandarin? 37, but we're still out of the 366. Did not take Spanish. Okay, so did not take Spanish. That is all of these people and all of these people. right? So it's everybody except the Spanish circle. So that includes all of this. So that comes out to 178 plus 27. 178 plus 20 out of 36. Oh, sorry, 366. 178 plus 27 is 205. I could, and you know what? It wouldn't be bad for me to write this. That this came from, just in case you see this later. 178 plus 27. I do count. Sorry, I don't count the 37 in that because the 37 people are taking Spanish. So yeah, it's just the 178. This group is not taking Spanish, and that group's not taking Spanish. In the end, these Venn diagrams come down to 4 regions. Notice there's 4 numbers inside there, and those 4 numbers are the different categories you can kind of be in. He or she took Spanish or Mandarin. Okay, so the big question on this is, should we count the 37? We're going to count the 124. We're going to count the 178. But do we count the 37? Okay, this is what I tell people. Suppose you're in both of those classes at the same time, and someone said, hey, are you taking Spanish? What would you say? You would say yes. If someone said, hey, do you take Mandarin? You would say yes. If someone actually came up to you and says, do you take Spanish or Mandarin? And you were in both, you wouldn't be so, you wouldn't be so rude as to say, excuse me, I take Spanish and Mandarin. You'd probably say yes. I mean, if you were, didn't want to get into a long argument with somebody, you'd just say yes. Yes, you are in both. And so yes, you are in the or. So the or counts the both. So really, I just have to add the one. You can think of this as a lot of different ways. You can think of 124 plus 37, because those are the 3 areas I see in the Venn diagram. There's a formula that doesn't read it that way. It's actually 161 plus 215 minus 37, but it doesn't matter. You're going to get the same total. This is out of 366. Actually, I'll write this down because some people will be bothered by this. 161 plus 215 minus 37. You're thinking, oh my gosh, wait, you said count the 37. Why am I subtracting it? Because I counted it twice in here. That's why I'm subtracting it. That's a longer story. If that doesn't make sense right now, that's okay. You don't have to worry about that. But what is 124 plus 37 plus 168? Oh, sorry, 178. That is 339. Another way to think about this is you could have done another back here. You could have done 366 minus 27. That's like everybody who doesn't take either one. 366 minus 27. Yeah, that's the same thing. Okay. There's some shading down here. Why do they? Oh, yeah, they're just telling you what these symbols mean. This is the and the or symbol. So, yeah, this means and. Well, I guess they set it off to the left, didn't they? A and B is this kind of rainbow kind of thing. It kind of looks like an N. Or you think of the letter U because that's technically the union of A or B. And notice, yes, they did shade the middle part when they did the A or B. Okay, so this is another Venn diagram. We have to actually do an example where they tell us things. We have to fill it in. There are 280. Again, I like to kind of say this out here. 200 take geometry. So geometry 200. I can't really put 200 in any of these places because I don't know exactly where that falls yet, because it's probably going to be split up. This entire circle is supposed to be geometry. And 66 take algebra 2. 66. And 45 are in both. So there we go. So if I'm going to figure out the rest of these bubbles, I know that the 45 plus this blank over here has to be 66. So 66 minus 45 is 21. And 200 minus 45 is what's going to go there. That's 155. And then what about the outside? I just want to complete the whole thing. If I added up all 3 of these discrete separate bubbles, that's 221. And I know there's 280 total. So 280 minus 221 tells me how many are on the outside. What's the probability of G? Oh, complete the Venn diagram. When it says complete the Venn diagram, I do really need all 4 numbers. I need the overlap. I need the separate things. I need the outside. This stuff, how should I show that? These numbers that I've highlighted in blue, technically, I don't think are part of the Venn diagram, but I don't think it's needed to be complete, but wow, they're really helpful because those numbers you really do need a lot when you do these kinds of things like this denominator here. G and A is the 45, and this is out of everybody, so this is out of 280. I don't mind, especially in this unit, I don't mind if you don't reduce that fraction because that 45 out of 280 actually gives me some contextual information that I don't mind seeing. So I will not laugh at you at a math party if you come up and tell me 45 out of 280 people take geometry and algebra 2 trig. Or is going to be everyone but the 59, so 280 minus 59, or I could add up those 3 little zones, and I actually had that number before, didn't I? 221 over 280. What's the probability? The randomly selected grader, 10th, it's way over there. 10th grader takes algebra 2. That takes algebra 2. Okay, so now this is my denominator. I have 10th graders who are in algebra 2, and that is out of 66 people. What's the probability that one of those 66 people also takes geometry? 45 out of 66. If you reduce that fraction, you can. It doesn't tell me where you got it. So, and it doesn't, these 45 and 66, these are actually people. So again, it doesn't bother me at all to leave that as an unreduced fraction. And the ACT and the SAT and the AP exam doesn't care either. All right, given this two-way frequency table, do we need to do this? Because we had a two-way frequency table before. I am going to save this one for class. Also, make this video shorter. Okay, and then, this is a three set, so this is a little trickier. All right, so there's 100 total that are going to these three things. All 100 had seen at least one of the following bands, X, Y, and Z. So there's nobody on the outside. All these zones, and there's just way more zones now, and some of this gets kind of complicated. Okay, so I've kind of done that one. I've taken care of the fact that there's a 0 on the outside. 14 of the visitors had seen band X and band Y, and of these, 3 had seen all 3. Okay, this is a great piece of information, that 3 in the center, because that's going to be part of all of the circles, and it's also part of these kind of footballs, so that's going to be helpful all the time. Okay, 14 of the visitors had seen X and Y. So the 14 is what that whole football takes up, but it already says, and it's careful, they were careful how they said this, of these, 3 had seen the all 3, so that tells us how that 14 splits up. It's got to be 11 and 3 to make the 14. 36 had seen X, so that's all of it, so I'm not ready to fill out the difference between those two sets yet. I just know they add 36. 55 had seen Y. Oh, that one I can fill in because there's only one kind of leftover cell there. So 55 minus 20 minus 14, that's going to be 21. So that whole circle adds up to 55. And 53 had seen Z. Oh, and now in Z, I can get everything. I can figure this one out because I know everything else. So 53 minus 23 minus 24 is 6. And now I have everything I need to do for X. 36 minus 14 minus 6. I'm adding some of those up in my head. And hopefully all those numbers should add up to 100. You could check that if you want. What is the probability that a visitor selected at random, so that's out of 100, had seen X but not Y or Z? Okay, you got to hunt around in the Venn diagram to realize that is the 16 that we just found at the end. All right. Okay, I just had to take a major pause. I don't know if that caused I thought it was back here, sorry. I'm doing this over multiple sessions in the video or not, but I'm ready to start the warm-up for lesson 4. So if I had to make a switch here, this actually wasn't that bad of a place. Okay, it's a warm-up, so of course we're going to do this in class. We're going to do this warm-up in class. Yeah. Oh, there's another warm-up. Okay. That's it? Okay, that's the whole thing. Was it back here? Oh, why am I doing that? Why does that keep happening? There was a picture. I know we on the. Here we are. Mutually exclusive events. Sorry. Mutually exclusive events is one of those kind of adjectives they use to describe the relationship between two events in probability. And, I'll just read it. Two outcomes are mutually exclusive that they cannot happen at the same time. So like heads and tails, or like being a junior and being a freshman. You can't be both those things at the same time. They are events, they are outcomes of probability experiments or trials or, results, I guess. And if you can't be both of those things, then those things are mutually exclusive. So use logic. Okay, that's really a great, that's a really great instruction. Use logic to decide if each pair of events is mutually exclusive or not. If they're if they're not, find at least one sort of counterexample. Find how you could be both. Okay, selecting a marble from an urn. Why is it always an urn? It could be a bag. And getting a white marble and a red marble. Well, if the marbles are all either white marbles or red marbles, you can't pick one marble and have it be both colors. So I want to say mutually exclusive. Another word, in AP Stats, we use another word for mutually exclusive. It's called disjoint. So you might see that word too. Disjoint. That's another way to say that. Maybe that makes more sense to you to say disjoint. That would be totally fine if you want to use that word. I'm going to use mutually exclusive. It's longer to say, but it seems like it's more typical. Throwing a die and having the outcome be a multiple of 3 and divisible by 2. Is there any numbers that are outcome of a die that could be both those things? Well, yes. Not mutually exclusive, because it could be 6. 6 is a multiple of 3 and it's divisible by 2. So that's not mutually exclusive. If you're going to make a Venn diagram, there would be some overlap. Drawing a card from a deck at random and getting a red card and a jack. Not mutually exclusive, because you could be a red card and a jack. Jack of diamonds, for example. There's one example that could be both things. Flipping 3 coins. Oh, by the way, speaking of deck of cards, on the theorem sheet, the one we always give you for geometry stuff, there's a section of that that's for this unit on probability. There's going to be a picture of the entire deck of cards. I thought it was on the last couple pages because I was just flipping through and I saw grid-shaped things. Anyway, you are going to get the deck of cards as an entire laid-out picture, so you will see those if you forget how cards work. There's not that many card questions in this unit, but whenever they show up in homework, it's kind of, if you're not familiar with cards, that's not something we want to hold you back, so there you go. Flipping 3 coins and getting all heads and all tails. So the cards can't be both all heads and all tails, so these are mutually exclusive. Okay. Yeah, there's a difference between mutually exclusive and independent. I think it's because, well, both of those kind of, I could call them adjectives. I don't know if that's true or not. They're both features that describe relationship between events, and they both feel like, and it's like the only two we have like that, and they also feel like there's some degree of separation, I think, when you say mutually exclusive, like there's some kind of, like they feel apart from each other, and independent, they also feel apart from each other, but they don't mean the same thing at all. Mutually exclusive means that there's nothing in the overlap, like there's nothing that's shared between those two outcomes. You can't be both. Independent events means you actually kind of have to be both. There has to be a both. That A and B kind of move around each other, and they don't influence each other at all. So when you look at, we're going to talk about tests for independence later, that there should be just as much A in B as there is A overall. So whether or not something is in B has nothing to do with the probability that it might be in A or not. So yeah, we will talk about this a lot in class, and this comes up a lot in problems and in discussion, and I'm sure it's going to come up more and more. But these do not mean the same thing at all. In fact, if events are mutually exclusive, they cannot be independent. So what I say in AP Stats is mutually exclusive and independent are mutually exclusive. Think about that. Okay, anyway, what if mutually exclusive events are happening? What is P of probability of A union B? What's the probability you're in A or B? That's just probability of A plus probability of B. The probability that you're A and B, of course, is 0. But if you're in, looking now at this side, at independent, if A and B are independent events, what's the probability you're in A or B? This is kind of tricky to do, actually. We have to count the probability of A plus the probability of B minus the probability of A and B. Like, we talked about this before earlier in this video. This is something you can kind of save for later. I think we're going to have a better theorem about that in another page. Here, there was this, so we're going to talk about it later. There's this little rule that says they're independent if and only if the probability of A and B happens to equal the probability of A times the probability of B. I think I want to talk about this way more in person. If I talk about it now, it's just going to take up a whole lot more video time. I've talked about it already, like when I was back on this page, I talked about how A and B should kind of not influence each other, and being in, anyway, I'm going to stop now. We will go over it more in class about that rule. Maybe I'll say this right now. Why? And yeah, we will do that more in class, but let's just apply this right now. Okay, example 2. One card is drawn from a standard deck of 32 cards. Let's talk about the events of being a diamond and the events of being a face card. Determine if they are actually mutually exclusive. So basically, can you have both at the same time? Could you have a card that is diamond and is face card? Well, of course you could. Not mutually exclusive. exclusive because you could have a diamond face card. You could have the queen of diamonds. That's a diamond and it's a face card. There's other examples. Draw a Venn diagram to represent the situation. Okay. We have the deck of 52 cards. There's 52 cards total. We have diamonds. And how many of those are? There are 13. And of face cards we have, oh yeah, there's 12 total face cards because there's Jack, Queen, King, and there's 4 sets of those. How many diamond, I think this is easier to figure out from the middle going out. How many diamond face cards are there? Well, there's Jack, Queen, King of hearts and Jack, Queen, King of diamonds. So that's 6, leaving 6 other face cards and leaving 7 other diamonds. How many cards are there on the outside here? Well, 7 plus 6 plus 6 is 13 plus 6, which leaves 33 cards on the outside. Okay. Determine if getting a diamond and getting a face card are independent. Okay. So the test we're using here is we're trying to find out if probability of A and B, is it the same as the probability of A times the probability of B? This is one of the, there's a couple different ones. This is one of the tests to determine are they independent or not. Oh, this is so good, you guys. Okay, so probability of diamond and face card. Let's just figure that out by itself. Well, the probability of getting a diamond and a face card, we can tell from the Venn diagram above, is 6 out of 52. The probability of diamond times the probability of face card is, well, how many diamonds are there? Well, there's 13 out of 52. And how many face cards are there? Well, there's 12 out of 52. So if I multiply these fractions, I get 3 out of 52. Oops, which reminds me that I messed this up. Oh, good thing, because I knew they were going to be independent. Yeah, diamond face cards, sorry, there's only 3. I messed up this Venn diagram. I was thinking red face cards. I don't know why I was thinking red face cards. So that's, whoops. How come I can't erase that? That should be that, yeah. How many oh, this is probably wrong too. Oh, no. Oh, no. Well, at least I figured it out now. You have to tell me in class. I messed this up. How many diamond face cards are there? 3. Jack, Queen, King of diamonds. There are 10 other diamonds. There are 9 other face cards. So let's do this again. 52 minus the other stuff. I should get 30 out here. Sorry. All right. So now I think everything's fine. So the diamond and face card probability is 3 out of 52. The diamond, I'm talking about this. The probability of being a diamond times the probability of being a face card is also 3 out of 52. Those are equal, so yes, independent. Okay, so as long as we're here, we just determined they're independent. Let me just talk about independence some more. Again, independent means that, like at a basic level, independent just means they don't affect each other. So one way to think about this, now that we're talking about cards, I think a good way to talk about this is, say I was drawing a card, and you really wanted it to be and I'm drawing a card and I'm not showing you, and there's you for some reason you really wanted it to be a diamond to play whatever game we're playing, and I say, hey, guess what? It's a face card. Like, does that have any influence? Is that independent from your prediction about whether or not it's a diamond? Just because I say it's a face card, are you more excited or less excited about it being a diamond? No, because there's just as many diamonds among face cards as there are diamonds in the entire deck. In other words, those things are independent. Knowing it's a face card or knowing it's a diamond does not help you predict whether or not it's the other thing. So that's, I think, one of the best kind of demonstrations of what independent means. Okay, and then calculate the probability of diamond or face card. Okay, well, now that my Venn diagram's right, I can say this. That equals all 3 of those zones together out of 52, which I just figured out, and that was 22 out of 52. And again, no, you don't have to reduce these fractions. I think this is so similar, we can save that one for later. Oh, it has part D too. Let's just do this whole thing all the way through part D. All right, last page. It's also a card one. Let me look quickly. Does this seem like something we could do together? I think so. I think we'll do that together in class. But complement we will talk about now. Complement is a different kind of concept. Complements are, well, it says here, it's everything but, sort of. So it's like not A. So if you're talking about one element, or sorry, one event at a time, either it happens or it doesn't. So the probability, sometimes the probability of something happen, like trying to calculate the probability that A happens is really hard to calculate, but calculating the probability that it doesn't happen is actually easier. So sometimes we try to do like a 1 minus kind of thing. So another thing you can say here is the probability of A is actually 1 minus the probability of A naught. There's lots of different notations for A naught. Here we did, you can say not A. So I've actually seen this, not A. I've seen A complement that way. I've also seen in the stats book, actually, it's like that. Oh, I think I think even I've seen this with a bar on top. So any of those things mean everything but A, or not A, or A fails. Okay, so let's do, this Venn diagram, because it has an example of some not stuff in here, here with the B. All right, so let's fill it out. So A is 0.4, not B is 0.3. So right there, I know already that probability of B is 0.7. So that's really the first tricky thing there. And A and B, that's in the middle here, that's 0.2. So I can fill out the rest of this pretty quickly. Whoops, that's 0.2. And this would have to then be 0.1. So the whole thing adds up to 100%. Find probability of B. Oh, yeah, I did that already. That's 0.7. And A or B, that's 0.9. That was actually pretty easy. And I think that's the end. Okay, I'll see you in class.